Okay. So I wanted to point out for a minute that in the area of 2D equations that we've been talking about so far, we've been implicitly assuming an underlying geometry is some sort of flat plane. But there's actually other interesting 2D geometries. Right? You can also consider differential equations on a sphere, which is sort of not that interesting.
Especially locally.
Yeah, well, everything locally is a flat plane.
Right.
But because we're going to let ourselves do sort of global things, the sphere is just not as interesting. But the more interesting one is the torus. Okay,
Asteroids.
So yes, so this is playing asteroids, right? So if you take a flat plane and you identify sides, top and bottom and left and right, so that if you come out over here, you go in over here, come out this way, right? So you come out on the other side. Yes, that makes sense. Then essentially from a torus standpoint, you are wrapping around you can wrap around this torus somehow in the hole around, or you can go all the way around the outside, right? So another thing you can do, right, is you can just sort of run around the outside. But that's not as interesting as running through the hole. And the natural, if you have theta 1 and theta 2, that run on the interval 0 to 2 pi, but then are 2 pi cyclic, right? These are the coordinates of a torus. So both of these angles run from 0 to 2 pi. And when you get to 2 pi, you go back to 0.
Right. Okay.
Right. Which is why I've denoted the intervals as closed on the 0 end and open on the 2 pi end.
Okay, that makes sense.
Right, because the 2 pi point I don't want to include because that would be an extra point.
Yep.
So 0 to 2 pi is the torus that we're interested in. And so we're going to look at differential equations that look like theta 1 dot is some f1 of theta 1 and theta 2. Theta 2 dot is some other function of theta 1 and theta 2. So we have differential equations of this kind. Are the differential equations on the two-dimensional torus where the coordinates have this feature that they're cyclic from 0 to 2 pi. So the simplest and possibly most interesting, or probably the simplest case, is to do something like theta dot. This is called coupled oscillators. Is omega 1 plus k1 sine of theta 2 minus theta 1, and theta 2 dot is omega 2 plus k2 sine of theta 2 minus theta 1. And this differential equation will wind you around on the torus. Okay. So this is, sort of an interesting one to play with. And you have a couple of different parameter choices, right? So you have choices for omega 1 and omega 2, and for K1 and K2, right? These are all kind of free choices that you get to play with. And you can explore a lot of the parameter space for that. Now, if you do K1 and K2 both being 0, then this is sort of the simplest delinked case. And you would have theta 1 dot is equal to omega 1, and theta 2 dot is equal to omega 2. So the way you would go about solving that is you would say this is d theta 1 ds, and this is d theta 2 ds. So if I did d theta 1 ds times ds times d theta 2, I would get omega 1 divided by omega 2, and then I could cancel out the ds's, and I would have d theta 1 d theta 2 is omega 1 over omega 2. Okay, so these are just two things that are oscillating, right? So basically we're looking at theta 1 is omega 1 and theta 2 is omega 2. So basically, like, this way it's oscillating and this way it's oscillating, and they're not necessarily related to each other. Now, even in this case, though, there's interesting mathematics. So it turns out that if so basically the dynamics here are going to be straight lines, right? It's on the torus. So with these k's being equal to 0, it just wraps around the torus in some sort of straight line. Now the question, though, is okay, let me write this way. You can prove all sorts of interesting stuff about what happens to the types of orbits. So it turns out that if omega 1 and omega 2 can be written in the following way. So let's suppose omega 1 over omega 2 is P over Q, with P and Q whole numbers. Not whole numbers. I want them to be
Integers.
Integers include the negatives. Whole numbers include 0. What's the one that include just the 1 through whatevers?
Would that be reals?
The reals are everything.
No, the
right?
reals
The
are
reals might have
everything.
all the decimals.
Yeah.
Positive. We'll just go with positive.
That's fine.
There's a math word.
I don't remember math 180
I don't remember
that much.
All right, so if you have this, then, so if this is the case, with this being the case, then all the orbits are closed. Because basically what happens is it'll wrap around the theta coordinate. So let's suppose that you have P is equal to 2 and Q is equal to 1, for instance. then it's going to go through omega 2 times. Excuse me, it's going to go through theta 2 twice every time it goes through theta 1 once.
Right.
Right, because it's going through omega. So P was basically omega 1. So omega 1 is running faster.
Mhm.
Right, so it's going to run through one of them faster than the other.
Twice as
But
fast.
it's going to run through twice as fast, but it's going to close up. Or if you have, P is equal to 3 and Q is equal to 2, then there's you find the least common denominator essentially, which in this case is 6, right? And so one of them runs through 3 and the other one runs through 2 orbits, right? And these are called knots. So this is a 3-2 knot. And the orbit kind of looks like you come around, up, through, around. So you're coming that way. Right. So you imagine tying a string. So on the torus, you've come around this way, out. No, you come around this way, under the back, around the top, under the back, around the front, under the back, and back around.
Yep. I see that.
Okay. And so you can have different types of knots in these. Okay.
Yep.
So on the other hand, so these numbers, right? Are rational numbers. If the ratio of the omegas is rational, which means you can write it as the ratio of integer values, then you get these knots. If not, we do not get closed orbits. The flow is dense, which means that each trajectory comes arbitrarily close to any point on the torus. So if we go back and you think about, the asteroids game, right? A 2-to-1 winding is going to look like that.
Yep.
Right? A 3-1 is going to have to do something like that. So if we have these rational numbers, there's no matter what the ratios are, there's always space between all of these lines. Okay.
Yep.
If the ratios are irrational, any point that you pick, basically you get everything's a line. It's going to come through here as lines, right? But any point you pick, it's going to basically fill the whole block. It's never going to repeat. It's just going to fill the whole block. And any point you pick, the flow will eventually get close to that point, which is not true if you have this sort of rational ratios. You can pick points which the flow doesn't ever get close to. Okay.
Yep. That
Now
makes
you can
sense.
keep studying this stuff. So this was all with K1 and K2 being 0, right? Once you couple them, you can get you might have a stable orbit in the coupled system, and then other orbits.
This is on irrational still, correct?
No. So this is going back to K1, K2, not 0 anymore.
Okay, so we have K2. Okay, that makes sense.
So this is going back to theta 1 is equal to omega 1 plus K1 sine theta 2 minus theta 1, theta 2.
So now we're not doing the simple case.
Yeah. And what
Okay.
you can have though is, and then you might have an unstable orbit as well. And then all the other orbits will approach the stable orbit. That makes sense. So you can have the situation where you have these stable orbits and unstable orbits, and then you can do all the things that you do with saddle node bifurcations to these guys. So at a given K1 and K2, there might be one stable orbit and one unstable orbit. And if you bring them together, then you can make them go away. And then you could just get this total randomness again. So the idea is that there's some more interesting dynamics that can happen in the different geometries than what happens in just the plane. So it's something to be aware of.
Right.
Okay, so there's that. So we're starting to sort of stop doing simple, easy stuff, right? So in 2D, in non-flat geometries, you can have a little bit more interesting dynamics than you have in flat geometry dynamics. But most of the stuff that happens in flat geometries carries over. Like you can still have a saddle node type bifurcation that happens, stuff like that. Okay.
Yep.
So now, if we want to do chaos, we need 3D ODEs that are nonlinear, or one-dimensional maps. So we're going to start in maps. Okay, so a map is some relationship which hops you point to point to point. We're going to jump from one point to the next point to the next point to the next point to the next point in one dimension. And so our map equation is x of n plus 1 is fn of xn. So in other words, I have x0 is my starting point. And then x1 is going to be f of x0, and x2 is going to be f of x1, and x3 is going to be f of x2, etc. But now x2 is f of x0. And x3 is going to be f of x0. So lingo wise, sometimes you'll see this as f2 of x0. Sometimes you'll see this as f3 of x0. Okay. But you should be careful. F2 of x is not f of x squared.
Right.
Because it's a composition, not a squaring.
Yeah, it's kind of like Newton's notation a little bit.
Yeah, so like if f is x squared minus 1, f of x would be x squared minus 1 squared minus 1. Yeah, that's right. Which is not equal to x squared minus 1 squared.
Right. Okay.
Okay. So you just want to be careful with that. Okay. So now in maps, you can have fixed points, which means that f of x star is equal to x star. So when you put the value of the function in, you get the value back. Okay.
Yep.
You can have a 2 cycle. A 2 cycle means that x2 is f of x1. But then if you take x2 and you stick it back into f, you get x1. So these are 2 points that are hopping back and forth between each other. Okay.
Yep.
And then you can have other cycles, right? You can have a 3 cycle or a 4 cycle or 5 cycle. These are just how many times you have to like stick the thing into there and get it to come back. Good?
Yep, good here.
Okay. So now, now the other thing that we can do with maps is we can also do stability of the map, fixed points. And in that case, again, you get to take the derivative. But instead of being positive and negative for the stability, so in flows, if the derivative was negative, then you were flowing towards to the left, and the derivative was positive, you're flowing towards the right. In the map case, and you can work through this. I don't remember exactly why this is the case. I mean, I sort of remember. The issue is whether or not you're moving further away from the point or further towards the point. and you take the derivative, and if the derivative size is less than 1, then you're moving closer to the point, and if the derivative size is more than 1, you're moving away from the point. So the stability of the fixed point in the map has to do with how big relative to 1 the derivative is at the fixed point.
Okay.
Okay, good enough. All right, fine. All
There's
right.
some obscure proof for that
Yeah,
somewhere.
it's not that obscure, right? It's the fact that you're bouncing around as opposed to moving continuously. So
Oh, okay.
if the next point is half as far away, then you're getting closer. If it's twice as far away, then you're getting further
Getting
away.
further away.
Right.
Yep.
So 1 is the dividing line as opposed to positive and negative.
Okay. That makes more sense. Yep.
Yep. Okay. Now the logistic map is our world famous chaotic map that we all like to look at and think about. So the logistic map is xn plus 1 is equal to r times xn 1 minus xn. And it maps the region from 0 to 1 into itself. So we're interested in points between 0 and 1. So over here is 1. And if I think about what this thing is, right, as a function, it's a parabola. And the height of this, the middle is at a half. Up here is 1. And the height of the parabola is going to be r over 4. And we're going to be interested in r values between 0 and 4. Okay, so for r values between 0 and 4, it maps the region 0 to 1 into itself. Okay.
Yep.
Now, you can get out and write a computer code to bounce the points along, and that's one way to do it. Another way to do it is to do something called a spider web construction. So let me show you a spider web construction. Let me try to draw this a little bit better. One, two, three, four, five, six. Okay. And then I want to draw a line. I want to draw a line that has a slope of 1. So this is my map. And my reference line is this line with the slope of 1. Okay?
Yep.
Now, the way this works is you pick any point you want. I'm going to start with that point right there. Okay? You go up to the function and over to the curve. Now, the reason this works is that the height is, this is my x0, right? X0 is my point down here. F of x0 is this height. This height is f of x0, right? I've drawn the function. So the height is f of x0.
Yep.
Right? And that is my point x1. By going over to the line, The point directly below this
Huh.
line is x1 because that
Okay.
line has a slope of 1.
Yep.
So now I want to do the map again. I should go up to the function. And if I go over to the line, that's x2. And I can go up to the function, over to the line, up to the function, over to the line, up to the function, over to the line, up to the function, over to the line. Now my line is a little bit past. I'm going to come down here. I'm going to end up in here.
Yep.
So I'm going to end up that at this particular R value. So remember, the height of the map is R over 4. So at the R value that I picked, there's a fixed point, it looks like, over here somewhere. So I end up at a fixed point. So what happens is my map drives me towards that fixed point. If I've done this correctly and my graph doesn't look great, right? But I pick another one over here, I could go up, over, and you can see I'm going to end up in the same spot.
Cool. Huh. And this is a way to just do it by hand.
It's a way to graphically see how the map iterates.
Right.
Okay. Now, if I draw the thing a little bit, it's going to be hard to draw this exactly right. It's possible to have a map. Here's my 1 line. All right, here's my slope 1 line.
Yep.
Here's some region of the map. It's possible to construct this thing where it runs around a box. And when you do that, you have a 2 cycle. You have 2 values. X1 and X2 that are mapping into each other. So X1 is going to X2, is going to X1, is going to X2, is going to. So you can see how you might construct a 2 cycle using this sort of spider web diagram. Okay.
What would a 3 cycle look like?
Oh God, how do you draw a 3 cycle?
Yeah, like I'm thinking a square makes sense, right? But
yeah, you
would it be some
gotta
weird,
so
like
the way
parallelogram
you
thing?
see how you draw a 3 cycle for the logistic map. So if you write down x n plus 3 is f3 of xn is f of f of f of xn. And then you plot out what this thing looks like. So you got f of x is r times xn times 1 minus xn, right? If you plot out what this thing looks like, it looks like something like that. And it cuts through here. And what you end up with, it's going to click this thing 1, 2, 3, 4, 5, 6, 8. Yeah, it clips through here a bunch of times. And then there's 3 points on here, like this point, and that point out there that end up mapping into each other somehow. Or actually, another way to look at it is that they are that those 3 points are fixed points of the 3 cycle.
Right.
Okay. All right. So I was just gonna pull up a Python file. It'll take a second to come up. I think it's just saved actually.
And if we were to plot the xn's as a function of the r values, that's when we
Yes.
start to see
That is where you start to see the interesting
the
stuff.
chaos.
Right.
Okay, that's the
Right.
real cool stuff.
So
Got
what
it.
you do here, so on this axis we're going to plot R. On this
Yeah.
axis we're going to plot X in.
Mhm.
And so the idea is that for each R, we have a different map.
Yep.
Right. So
Oh, and where the chaos stops is where you have the 1 cycle, 2 cycle,
2
3
cycles,
cycle.
and yeah, so you
Oh,
start to see
okay.
this stuff,
Okay.
right?
Yeah.
So try to share. Yeah. No. Guess I'm sharing that. Okay, so you should be seeing a Python file.
Yep.
So, standard starting stuff. Here I've defined my logistic map and I'm giving it a value of R, right? So now if I stick in, so here's what I'm doing, right? I'm starting with some random X value. Okay. I'm going to start with R being 2. I'm going to run the logistic map 100 times. Okay. And then I'm going to make a list where I run it, say 1,000 more times. I'm actually going to run it 1,000 times and get rid. So I'm just going to run it and see what it does for a while, because that's going to clear it out of whatever weird thing it's doing. And then I'm going to run it another 1,000 times. And then eventually I'm going to plot for the R values, all the different X's that I get.
Mhm.
And so if I run this, and then what I'm doing is I'm putting the last 20 times of that 1,000 times I've run it. So I've run this map 2,000 times.
Right.
I'm going to look at the last 20 values. And I'm going to plot some things.
Mhm.
Okay. So at R equals 2, when I start at 0.2,
you're getting towards 0.5.
I'm getting towards 0.5 and all the points are right there. All right,
Yep.
well, what happens if I start at 0.7? I also end up at 0.5. What happens if I end up at 0.34? I also end up at 0.5. So this value is the fixed point. There's one fixed point at R equals 2.
Yep.
It's stable,
Mhm.
and everything runs into that point.
It's just driving right to it.
Okay, now that happens until you get to R equals 3. If I do R equals 3.101 and I run it, okay, and I look at the last 20, I have these 2 points.
And you're oscillating between them.
And if I
Or you're
look at
cycling.
these, right, it's just bouncing back and forth between those 2 points.
Yep.
Okay.
Mhm.
And that continues for a while. So now they're spread out a little further apart. Okay.
Yep.
I'd like to make my axes have the same size all the time. Python axes limits. Axis limits. How do I do that? XLim. That's not what I want, I don't think.
Yeah, I can't remember off the top of my head.
Maybe set Y lim might work.
Because it's automatically scaling them, right?
Yeah, that's what I want to make it stop doing.
Mm-hmm. They got a
PLT dot-
figure size up there.
Yeah. Figure Y lim PLT
They did dot set X
dot
lim.
set Y lim maybe.
Yeah.
Set underscore Y lim
Underscore Y lim.
0 1. No, wasn't supposed to do that.
I didn't do that.
That didn't work.
It gave you an error though.
Said Y limits. Matplotlib.
Oh.
Oh, I needed parentheses. Maybe. So instead of
Yeah, instead of square, you do.
I needed that maybe. Oops. Oh, come on. Oh, it's still not right.
No attribute set Y lim.
There we go. Okay. So they're getting further apart.
Mhm.
Right. And then the interesting things start to happen at 3.5. So at 3.51. So now my R is 3.51.
Yep. Can see the cycle, but it's
Every 4 numbers are
Mhm.
cycling. And so you have these 4 points, which is hopping between. Okay. Now, if I were to not do this full second set, so let's suppose, see, what's happened is I'm starting at 0.34. I'm running it 1,000 times, runs it onto those points, and then it lands on those points. So that 4 cycle is a stable 4 cycle, which means no matter where I start, after a while, I end up on those 4 points.
Yep.
That makes sense?
Mhm.
And so what you're having is something called period doubling. It starts with 1 stable point and then it splits into 2, a 2 cycle. And then those 2 cycles splits into a 4 cycle.
Right.
Okay. But then it gets wacky shortly after that.
Because it only can split so much.
Oh, what did I just do? Oh, well, that was bad. All right. So at 3.55, it's still good. But at 3.56,
Still looks like it is.
Yeah, where am I need to go? 3.6 maybe?
There we go.
So now I've got this whole thing, and basically there's nothing in this list that repeats.
Right.
So basically, this is something called the period doubling transition to chaos. So it doubles, it becomes a 2 cycle, 4 cycles, 8 cycle, 16 cycle, 32 cycle, 64 cycle, and very quickly devolves into a completely chaotic pattern, which means these points are not repeating whatsoever. But then interesting stuff starts to happen later.
Because they come back together, right?
They start to come back together, and what you pick up is a 3 cycle.
Because we started with a 2, period double to 3, and then each
Yeah, all
one
right.
will
So the 2
double
cycle
again.
goes through its thing.
Yep,
And then a little bit later, a 3 cycle shows up.
as it converges back.
So it comes back and
Yep.
it's hopping now between 3 points.
Mhm.
And if I increase the value a little bit more, it's now hopping between 6 points.
Because each
Because the
one of
2
the 2,
cycle
yeah.
has split again.
Yep.
Okay.
You
So
go
the
3 to
3
6.
cycle becomes a 6 cycle, becomes, and then it period doubles
Mhm.
until, you know, you get back into the mess again.
Then come back down to 4.
But then other cycles start to show back up.
Right.
Okay. And so if you make a plot, so we were to make, instead of doing these X's and R's as single lists, if I made these matrices,
Yep.
and so on each, so the first column was a given R value,
Mhm.
and then I plotted all those points as matrices, I could fill this thing out, and
As
that's
R
this picture
values.
that you get.
Yep.
Right. So the classic picture of the logistic map is this period doubling to chaos, where the stable limit cycles double up, go chaotic, then you drop back down into well-defined stable behavior, and then it becomes chaotic and it drops back down to well-defined stable behavior, stuff like that.
Right.
Okay, so I'm gonna stop
Is that
sharing.
also called the Feigenbaum attractor?
Yeah, so this is what the Feigenbaum was studying this stuff and noticed a whole bunch of patterns in this. So I want to make my screen go like this.
And that equation arises from like tons of random stuff. Just
Yeah, but the thing that's interesting about it is that, so we have, this goes from for a while, and then it
Yep.
doubles, and then doubles, and then these guys double, and then we have these chaotic region, and then we have this 3 cycle that shows up, and then these double, and then they double on top of there, and then we get the chaotic region again. We get these different windows that open up inside of here. So now Feigenbaum was one of the main guys who was studying this type of stuff. And amongst the things that he discovered was this idea of universality in chaotic maps. So he studied not just this attractor, but all maps that have period doubling to chaos. And what you do is you define Rn to be the R value at the nth doubling, Rn minus 1, the value before, and plus 1, the value after. So this is the first R value. So if Rn is the first R at a 4 cycle, this is going to be the R at the 2 cycle, and this is going to be the R at the 8 cycle. So it's the value of R where the first 4 cycle, 2 cycle, and 8 cycle show up. Okay. Good.
Yep.
And then you make the following ratio. You do Rn minus 1 over Rn plus 1 minus Rn. So in other words, this is the distance between the current one and the previous divided by the distance between the next one and the current one. So if I'm looking at it as this distance here this is Rn, this is Rn minus 1, and this is Rn plus 1. Right, so up here, this down here is the denominator. Right, that distance is the denominator. And this distance is the numerator.
Okay.
Okay. And you take the limit of that quantity as n goes to infinity. And you call that delta. That number works out to be 4.669.
Yes, I've heard of this number.
Which for a while was the code to room 278.
Oh, I remember the code. I didn't know where it came from.
Yeah.
Okay.
I set the code to be the Feigenbaum number a semester I was teaching this class. It's like, okay, that'd be clever. Let's see who gets the reference. Right. So this is one of the first Feigenbaum numbers. There's a couple of these numbers that Feigenbaum found. And the idea is that this number of the period doubling transition to chaos is true in any map that has one parameter that has a period doubling transition to chaos. It's true in the logistic map, it's true in the tent map, it's true in all these different maps which have these same properties. And so this is a universal irrational number. Right? The number is irrational, it doesn't have a limit, right? But all maps that have period doubling have this behavior.
And they map physical things that happen.
Yeah, and to some degree they map some sort of physical things that happen, right? So there's
rabbits breeding and yeah.
All right, so what else is in my notes? Yeah, so we kind of went through the stuff in these notes. Yeah. So there's a bunch of other maps that you can do. You can study the 3 cycles, the 4 cycles. There's a way to think about dimensionality with this.
Ooh.
And the Lyapunov exponents. I'm trying to remember this.
We touched on Lyapunov already with
yeah, so there's a Lyapunov exponent, which is basically how fast neighboring trajectories are diverging. And in chaotic maps, the idea is that if the map is chaotic, points that start next to each other won't end up anywhere near each other.
Yeah,
they're just going to go to wherever they go. They're not going to map into points that are near each other. As opposed to if you have an attractor, or if you have a stable cycle, random points that you start with will end up on the stable cycle.
And the double pendulum is kind of a good example of the Lyapunov exponent. You know, you experimentally can't get the same result.
Yeah, there's some other ones. Yeah.
Okay.
Cool. Yeah. So this is the type of stuff that you can do with this stuff. So this Feigenbaum numbers is any unimodal map that has the 2 n cycles. You get this Feigenbaum number for.
And there's no explanation as to why, it just is one of those.
Yeah, I mean, it seems to be this property of these maps.
A lot of weird stuff like that in physics.
Seems to be a what is. Yeah, I would go with it. It's a what is. All right, cool. So that's what I've got to say about maps. Cool stuff. Maybe next week we'll do we'll do chaos in 3-dimensional flows. So we'll do Lorentz attractor and stuff like that.
Yeah, sounds great.
Cool. I will stop recording.